make this too hard. First, hearing you debate when I walked around is kind of funny. To lift the barbell, I have to apply how much force upwards?
More than 100 newtons.
No, 100 newtons.
Yeah, so it's first.
That'd be, you could apply more, but that would be throwing it upwards. Because by the time it got up there, you would have done more work than gravity, and it would have a change in kinetic energy. You don't need that. You just need to lift it. It doesn't have to be moving when it gets to the top. Now, I get that means that you have to get it started, so you have to apply a little more force than 100 newtons to get it started moving upwards. But to maintain it moving upwards just takes 100 newtons. Gravity's acting downwards the whole time, of course, too. 100 newtons. So there's the work done by you, and then there's going to be work done by gravity. The work done by you is what we're worried about here. You're the one trying to work out. Gravity's not working out. You're working against gravity. So you have to apply a force over some displacement, and we need to determine how much of that force is in the direction of motion. Those are the three things. If you didn't know about those three things, what are you waiting for? Write that down. This is what you were asked to do. How much force do you have to apply? How far did the object move because of that force? And how much of the force was in that direction? Those are the three buckets that are here. You had to apply 100 newtons of force to get the weight to go up 2 meters. And hopefully you pushed upwards. That would make the most sense. Now, as I watch you guys, anybody waiting to start writing until I write, that seems wrong. The same three buckets exist here. Gravity's pulling with 100 newtons of force. The weight still goes up 2 meters. But this time, gravity's pulling downwards, but the weight is going upwards. So the amount of work done by gravity is negative. So you do 200 joules of work, but gravity does negative 200 joules of work. So the net work done is 0. That's important because you're not trying to change the kinetic energy of the bar. You're trying to lift the bar up, then you're going to bring it back down. You're going to lift it up again. You're going to do repetitions here. And every time you do a rep, you do 200 joules of work on the bar. Now, anybody who knows a little bit about working out, and there's a few people in here who look like they do, and a few people who look like they should learn. I wasn't calling anybody out. Wow, Garrett, did you see that?
Yeah, I did see that.
This is your friend, maybe.
Not anymore.
Clearly. You understand that the return rep is almost as important as the outgoing rep. You're supposed to synchronize this with your breathing. Let's just make it easy. Let's just say for the time being, you get 200 joules of work done every time you lift the bar. The problem is that the candy bar is 200 calories, which if you haven't done it yet, you have to multiply by how many joules there are per calorie. Those are big C calories. So if I do that, so if you'd like to know how many reps would be necessary to burn off that candy bar, there you go. That's an unreasonable way to probably burn off calories. But people who lift weights don't lift weights in the hopes of burning off calories. They want to tear muscle fibers, and so that they can build stronger striations, which seem to bulk up their muscles and make them stronger. If you're trying to burn calories, you probably want to do something that has more repetition to it. But that's the whole point. Every one of those machines at the gym, if you've ever been to the gym, and a few of you look like you should go, if you looked at any of those machines, they all are the same. Have you noticed? They're all lifting a weight somewhere. And through some set of cables, you're pushing in some direction. But there, at the end of the day, weights go up or down in the machines. Now, if you're doing free weights, of course, the only way free weights work is to work against gravity. All of them are the same. You must arrange yourself in some position to focus on the muscle group at hand. All of your machines that are designed for cardio are designed to more efficiently consume calories. And you can probably put together pretty easily how they figure out how many calories you've consumed. They can measure force. They can measure how fast the pad is going underneath you or how fast the cycle has been spinning, how much force you're applying to the pedals. All those cardio machines work in the same way. Now, that's not a good equivalence for how you burn calories, by the way. They're not even close. VO2 max is currently the most accepted standard for how you burn calories. And it has to do with the consumption of oxygen when you're respirating. And anybody who works out probably understands a little bit of that. Anybody who's wearing a watch that does that, it's estimating it based on heart rate. All right, as I see it, there are 3 potential forces acting on the box. Each one of them has the ability or the capacity to maybe do work. So of those forces, I think we've got weight, 100 newtons. There's a normal force. Don't know what that is. And then there's me pushing on the block with 75 newtons of force. And I'm supposed to figure out how much work is done by the box, how fast they're going at the top, whatever. You have 3 tests. The work done by your 75 Newton force, work done by the normal force, and the work done by gravity. You're asking me to do this, but I don't want to do the work. You can do it. It should be 3 buckets, so I know who to ask and not get the answer. I walked around, remember? So let's walk through it. The first bucket is force, second bucket is displacement, the last one is the angle between the force and the displacement. So we'll start with the 75 Newton force. There, I did my part. What's the displacement? What's the angle between the applied force and the displacement? 0. I'm pushing in the direction the box is going. Excellent. There's your low-hanging fruit. That's the easy one. Do we know the size of the normal force?
No.
Could figure it out, couldn't we? It's got to be mg cosine theta, where theta is the angle of the ramp. Has to be. Because we've done enough ramp problems where I'm pretty sure that's what it is. And if you haven't memorized that, why are you waiting? So I can give you a quiz on that tomorrow? Because I will. You should know that. I'm done playing around with that kind of stuff. It's not necessary to know it. Not in this problem. Because I know that the normal force can't do work on this problem. The normal force is perpendicular to the ramp, and the box slides up the ramp. The cosine is going to be 90 degrees. Doesn't matter what the normal force is. If cosine's 90, then it's not doing any work. It's not in a direction of motion. But I know the people who are hastily thinking that they didn't know that should be writing it down. We talked about that yesterday. The last one is the work done by gravity. Looks like gravity pulls downwards with 100 newtons of 100 newtons of force. And the box still goes 15 meters up the ramp. Looks to me like there's 110 degrees between the downward force of gravity and the direction of the ramp. I'm talking about this angle right here. Do you see why I'm choosing that angle? Gravity is downwards, and the box is going up the ramp. The ramp is 20 degrees. If this was 90, then this little extra 20 degrees plus 90 gives me 110. Bless you. Yeah, I expect you to do that little tiny itty bit of geometry. Now, you didn't have to do it this way. You could have done mg sine theta as the force down the ramp. You could have broken it into components. And you still would have made this 15, but this time it would have been cosine of 180 degrees, where this is 20 degrees. You could do that. That would have worked too. That's the force of gravity down the ramp, the component, the same thing we did for months. I don't care which one of these you do. The answer's the same. Prove it. Prove it to yourself. I don't need to prove it to me. You should. Make sure you understand that the physics doesn't matter. It's the same physics. I think it's easier to do this one. I don't have to break it up into components to do that one. But this will work just fine. Yep.
Why is the first angle 0 degrees again? Cosine 0 degrees.
We applied that 75 newtons in the direction that the box is moving up the ramp. So it's in the direction of motion. Yep.
When I did this, I used, for the work of G, I used the angle of 250 because I did 270 minus 20, thinking of the unit circle, and it worked.
Be careful.
Yeah, I was about to say, like, even though it worked, it wouldn't work in most occasions, would it?
I hasten you to always use the standard set by your pre-calc class where 0 has to be in a certain direction. I would set your angles based on the direction of the acceleration. I think
So,
you'll
like, zero
find
would be the
up the ramp. Yeah. If it were me, that's how I would do it because the displacement's in that direction. And we're basing these measurements there. I would not become fixated on using the unit circle. You'll be disappointed. All right. I think that's all I have to do. You add those together to get the net work. We got that far yesterday, right? And we set that equal to the change in kinetic energy. So you can figure out how fast the object's going using that. That's plug and chug. I don't feel all that particularly interested in doing that. I want to continue this. I really wanted to add something to it. I need some time. So I'm gonna ask you to try something. And the first thing I'm going to ask you to try is very straightforward. But I don't know. I'm a little bit concerned. Here's what I want. And this will take you a few minutes, but you should be well equipped to do this. I'd like to know how much energy is necessary to put the box at the top of the ramp. And then I would like to know how much work does gravity do sliding the box back down the ramp. There we know what I'm asking. I'll say it again. I would like to know how much energy is required to lift the box and put it at the top of the ramp. Straight up what you just did. And then I would like you to tell me how much work is done by gravity bringing the box back down. Straight up what you just did. I think you can do it. I'm going to call on 2 people to give me their answers. One for question A, one for question B. And it's going to be the quiet folks I never call on. So I'll say it again. how much energy does it take to lift the box up, put it at the top of the ramp, and how much work is done by gravity bringing it back down. All right, that should be about it. That's all the time I want to give you guys. All right. So let's think. Emma, can you give me one of the answers?
For the work done by you, 250 joules, and then the work for gravity was negative 250 joules, and then that cancels out, and then the kinetic energy is zero.
Okay. I think we have a little bit of a problem. So which one do you want to work with? We'll just do one of them, you and I. So either the box sliding down the ramp or the box being lifted up to the top of the ramp. Lifting it up. How much force do you have to apply to lift the box? Okay. So we're lifting the box upwards by applying a 50 Newton force. How far upwards does the box go? What? I don't think it's 5. The length of the ramp is 5, but I don't think this height is 5 meters. I didn't give you this height, but I think you have the tools to find it. You know what I'm saying? Okay. So that'd be 5 times the sine of 20 degrees. Excellent. So now, when we talk about the cosine, we're talking about the angle between what force you apply and what direction the box goes. What do you think we should use here? I think we should use 0. So this is the work you do lifting the box. Questions about that? All right. Gannon, can you help me do the next part?
Work of gravity.
Yep.
So it would be 50 newtons,
Okay, force of gravity, 50 newtons.
and b times the same displacement, 1.7.
I don't think so.
Oh, this is the net point?
Yeah,
Oh, sorry.
that's okay.
Times 5.
5 meters, perfect.
And then, so it's cosine of 70 degrees.
Be the cosine of 70 degrees. We're looking at the angle between the displacement, which is this way, and the weight, which is this way. That angle here is 70 degrees. What do we get here?
I got 85.5.
85.5, yeah. That's right. Now, I want to impress upon you something that's important here. It took 85 joules to get the box to the top of the ramp. And it took 85 joules to bring the box back down from the top of the ramp. Clearly, the force involved here is the force of gravity. The fact that these are the same isn't a coincidence. It's because conservative forces are path independent. The force is conserved, which means the amount of energy necessary to work against gravity or with gravity is the same regardless of the path taken. I'm going to say that again because it's important that you understand this idea. Regardless of the path taken, the work done by gravity or against gravity will be the same. The only limiting factor is the change in height. That's the limiting factor. That's what decides. So whether we take the long way around or the short way, same amount of work is going to be done. Let me give you a for example. Not all of it, yeah. I want you to imagine the same scenario with a slight difference. So what if the box could take one of two routes to the bottom? So the box could slide down the straight slope, or the box could slide down that curved path. In which case would gravity do more work? Going down the straight spot or going down the curved spot? Neither. It would be the same. The change in the amount of the amount of work done by gravity in bringing the box is based on the absolute change in height. That's the limiting factor. Whether it takes that curved path or takes the straight path, the box still reaches the ground. And because this is path independent, the same amount of work will be done. Now, there's a lot of implications here. Things that you're not thinking about that I need to highlight for you. Whether it takes path A or takes path B, the net work done is going to be 85.5 joules, just like before. Assuming it's a 5-meter ramp and the box is, whatever it was, 5 kilograms. Is that what we said? Still going to be 85.5 joules. Yes, sir.
So if there's friction, wouldn't the work be higher for gravity?
Lower, actually. Well, the work would be the same for gravity, but friction will have taken some of the energy away. So the net work would be less. We'll do that problem in just a minute. Now, here's the implication I want you to think about. Same change in kinetic energy, if this is the only thing doing work, which means both boxes reach the bottom at the same speed. Say that again. Both boxes will reach the bottom at the same speed. The paths aren't the same, though. They'll have the same speed at the bottom because they have the same amount of work done by gravity, and therefore the change in kinetic energy will be the same. That also suggests that if I just drop the box off the back, it'll hit the ground at the same speed. It's path independent, which means if gravity is the only thing doing work, it doesn't matter what path the object takes to reach the ground. But don't think they're all the same. Between path A, B, or C, in which case will the box hit the ground first? C, for sure, yeah. It's the shortest path. But don't think that's the answer all the time. If it was between A or B, in which case would it reach the ground first? This one's harder. This takes real insight. It would be B. And the reason it's B is because it's steeper in the beginning, so it will get up to speed faster. And therefore it gets to its top speed sooner than the other one, so it reaches the ground first. However, they're all going to have the same change in kinetic energy. Now again, we're assuming something here, that there's nothing taking energy out of the system. If there was friction, that changes things. The path will have something to do with it. Friction is a non-conservative force, which means it is path dependent. That's what the real difference is. Longer paths expose your object to more friction over time, and therefore have a chance to take out more energy. Friction is a non-conservative force. It is path dependent. The longer the path, the more energy it can take away. Gravity, however, is path independent. It only cares about changes in height.
Could you repeat that last one?
The gravitational force is path independent. It only cares about changes in height.